Good evening, everybody, and a Happy New Year to everyone gathered in this lecture theatre. I'd like to welcome you to Lecture 3 in our series on cosmic revolutions. And the title of tonight's lecture is Structures in the Universe. Our universe is a richly structured place. Now, that may not seem a surprising statement to make on the face of it. After all, we know quite a lot from our night sky. We know about the stars in the foreground, in the near field from our own galaxy, and we see patterns in those. And we see galaxies beyond, and even more exciting patterns of galaxies beyond that. So the idea that structures in the universe are a thing isn't surprising, and it won't come as something new to us. I'm showing a projection of some of the things that we can see in the night sky in what are called galactic coordinates. The plane of our galaxy is shown along the centre of the image that you can see here. On exactly the same projection, I'm going to show you what the cosmic microwave background looks like, which I described in quite a bit of detail in the first lecture in this series on cosmic revolutions. That was the lecture called Early Universe. So what I want you to appreciate is that this is how the universe was, and this is how the universe is, at least as far as an observer on Earth is concerned. The projection is exactly the same in a coordinate sense. But in this image, looking much, much further back in time, nearly 14 billion years back in time, the universe was a much more smooth place. It was a much more homogeneous place. The differences across this image are very, very subtle. The temperature scale at the bottom, temperature being how we represent the differences in the physical properties in the universe at these early times that I described 2 lectures ago, are very subtle indeed. On the left-hand side, the extreme minimum is minus 300 micro degrees Kelvin, and on the right-hand side, plus 300 microdegrees. So very, very subtle variations indeed. If we could have a swimming pool that was as smooth as the universe used to be, it would be very, very flat indeed. To be comparably smooth, the largest ripples on a swimming pool of average depth, a few meters, would be less than 1/100th of 1 millimetre high. That's how smooth the universe used to be. So against that backdrop, in that context, the fact that the universe is highly structured now perhaps is a little bit surprising after all. The universe used to be a much more homogeneous place, but now, whenever and wherever we look in the night sky, you would not use the adjective smooth. You might use the adjective lumpy or structured. Here's a view of the night sky in the constellation of Carina. You can see a little bit of a cluster of stars over here on the right, and a little bit of nebulosity, gas, in the top left. This was an image taken with one of my global JetWatch cameras. So that's looking at stars within our galaxy. They are pretty lumpy. But when we start to look beyond our own galaxy, ideally with the assistance of a space telescope, then there is no doubt whatsoever that the universe now is a very inhomogeneous place. Matter is very unevenly distributed. There are all these lumps of matter, known as galaxies, and in between, not so much matter. The universe now is a very inhomogeneous place. So how on earth did we get from that amazingly smooth state of affairs to this amazingly inhomogeneous state of affairs, where there are all sorts of different galaxies throughout the observable universe? Where did these structures come from? How did we transition from the smooth, homogeneous state to the very lumpy, inhomogeneous state with the structures that we see today? Well, I want to begin by just touching on how one star forms. If you have a lot of gas, and if it's not too hot, and if there's enough of it, so there is quite a lot of mass, then you have the necessary ingredients to be able to form a star. Large masses of gas are involved. And let me remind you at this point what the mass of our nearest star is, the Sun. The mass of our Sun is 2 times 10 to the power of 30 kilograms. So you have to have a lot of mass. And if you have got a lot of mass, and we've got the whole universe here, then you can hope to form a star from it. So let's imagine we've got lots of primordial gas, and there are inhomogeneities, lumpiness, unevenness in the distribution of that primordial gas. And now think about the temperature of that gas. What does it mean for gas to be hot? When you've got gas that's hot, it means the atoms, or perhaps the molecules, within that gas cloud are whizzing around at great speed. That's what it means for a gas cloud to have a high temperature. A gas cloud at low temperature would have the atoms moving around at a much more leisurely pace. Those atoms have less thermal energy and hence less kinetic energy. So if you've got a big mass of primordial gas and it's not too hot, then a competition can begin. There's a process which we call Jeans collapse, which describes the competition between the pull of gravity that the centre of mass of that gas cloud will experience as it gravitationally attracts all the other mass around it, versus the thermal kinetic energy of the atoms wanting to whiz around and do their own random exploration of space without being drawn in under gravity to collapse into something they can't necessarily escape from. If you have a gas cloud that is cold and is dense, that is favourable to collapse. Gravity will win out over all that thermal energy. When the gas starts to coalesce and become denser still, as long as it's sufficiently dense, then gravitational collapse is inescapable. But then something different happens. The gas becomes very, very extremely hot. And a process that I talked about in my second lecture in this series on cosmic revolutions, entitled Atomic Universe, about a process called fusion, that process of fusion then takes place. If you've got a mass of gas that's where fusion has been ignited because the temperatures are so high, you have got a star. That, in a nutshell, is how stars form. So stars clearly do form all across the galaxy, all across the universe. But in reality, they don't tend to form as isolated systems. Typically, most of the star formation that we see in our galaxy today or in other galaxies is in the context of what are sometimes called stellar nurseries, regions of ongoing star formation. This will, I'm sure, be a very familiar view in the night sky, at least for those of us who haven't had the cloudy weather that we've been having in the UK in the past few months. This is, of course, Orion, and I want us to just zoom in on the central bright region in the sword of Orion. You can actually see with the naked eye that that object is a bit fuzzy and not very star-like. If you zoom in with a telescope, and I used my telescope in India that's part of the global JetWatch network, then you see, of course, the famous Orion Nebula. This, in fact, is the closest region of massive star formation to our own solar system. The very brightest region there, not really resolved in this particular image, is the trapezium set of stars. It's a very young cluster of stars, very, very young, very, very hot, and irradiating all the gas around it that has yet to collapse under gravity and form stars. Indeed, the presence of those bright stars right in that central trapezium region is offsetting the other gas around it collapsing under gravity, because it's heating up that gas and it's helping it in the fight of gravitational attraction causing collapse and thermal energy which preserves the gaseous state. So stellar nurseries are regions of high activity. Stars form, they can stop other stars forming. It really depends on how dense the region is and how massive some of the stars are. But if you do get an entire group of stars forming together, and it can be larger than just the very small number in the Orion Nebula that I just mentioned, you can get something that is akin to a mini galaxy within our own galaxy. You can get a cluster of stars. So there are predominantly two different types of clusters of stars in our galaxy, the Milky Way: globular clusters and open clusters. I'm going to talk about the globular clusters to start with. These are pretty remarkable. They have a lot of stars, and a lot here is 1 million or so, some large number like 1 million. You get a lot of stars very similar in age, meaning they all formed around the same time. If you get a lot of stars all forming around the same time, they're not all going to be, even though they're born in the same litter, as it were, in no sense are they identical siblings, far from it. If their masses are different, the more massive ones will evolve more quickly, the less massive ones will evolve more slowly. And so it's a very interesting laboratory to be able to study stellar evolution from the same assumed starting point. And that's really quite important. Something else that is a feature of globular clusters is that because the most massive stars within will evolve most quickly and potentially explode in a supernova, that blast wave, that shock wave from the supernova explosion, will do something else to any residual gas which hasn't quite collapsed into stars. It'll sweep it out the way. It will clear out any other gas. And so you can get a very unusual environment within a globular clusters. Just a big bunch of stars, self-gravitating because they're all pretty close together, all formed out of the same massive primordial gas cloud, but free of gas that could form any other stars in the future. So quite a remarkable environment if you've had a sufficiently massive star at the centre that it has evolved quickly and gone supernova. If you have that, it will put a stop to any further star formation because it will have wiped out any residual gas. But gravity will continue to be highly relevant to that cluster of galaxies, regardless of the presence or the absence of any residual gas that never made it into stars. And so we do see these really beautiful structures throughout our galaxy, not just in the disk of our galaxy, but throughout its halo, these mini galaxies, these galaxies within our galaxy. So what we're seeing on the screen here is Messier 22, a globular cluster in Sagittarius. It's about 11,000 light years away from the solar system. It's one of over 150 globulars inside our galaxy. So there aren't a huge number of them, but there are enough of them for it to be really remarkably interesting to study them. They can be very old because they're really very stable. Once they've formed, because they're quite tightly bound under their own gravity, they're pretty resilient to anything else that they happen to sort of rock up past as they orbit throughout our galaxy. They're really remarkably stable. This is a picture of Omega Cen in the Centaurus constellation, of course, taken by my colleague on the Global Jet Watch, Stephen Lee. This was discovered in 1677 by Edmund Halley. But of course, with the superior optics of today, I'm sure you could get a pretty good photo of this just with a smartphone. Not quite as good as the one I'm showing you, of course, but certainly a sense that it's a resolved collection of stars and not at all something that you could ever confuse with a star. From one side to the other, depending on exactly where you define it, it's something like 150 light years across from one side to the other. From the solar system, that's quite a long way, 17,000 light years. This particular globular cluster is a big one. It's the largest one in our galaxy. It contains about 10 million stars. Beautifully pristine, almost spherically symmetric, free of gas, and a fascinating object to study in its own right. This is a rather more weedy version. In fact, this one isn't really a globular cluster, although it's quite compact, as clusters of stars can go. This one actually counts as an open cluster. There's less than, or fewer than, 1,000 stars in this particular open cluster. And an open cluster is much more sparsely populated. It's much less, the stars within it are much less strongly bound. And that means they're much less resilient to any other gravitational inhomogeneity that they might orbit past as they process through our galaxy. So you don't tend to see very old open clusters because they're not resilient. They're not stable against gravitational perturbation. They're still beautiful, though. Here is another one. This is NGC 6250, shown on the left there. Fewer stars indeed, and next to Barnard 86, which is a dark nebula, where it's basically blotting out, absorbing all the light behind it. So open clusters can still be very interesting to study, but they're different, they're much more fragile than the globular clusters. So let's now go up a scale and let's start to think about galaxies and the structures that we see in galaxies. So this is a beautiful image of the night sky taken from Australia. And without wishing to be hemispherist, the sky in the southern hemisphere is superior to the sky in the northern hemisphere. Why do I say that? Well, it's got the centre of our galaxy, and that's got a lot of cool stuff going on, but it's also got two galaxies, other than the Milky Way, other than our own galaxy, which you can see with the naked eye if it's dark enough. These two galaxies indicated by the arrows here. So that's obviously the plane of our own galaxy, the Milky Way, and these two galaxies are, the lower down one is the so-called small Magellanic Cloud, and this one slightly further up to the right is the large Magellanic Cloud. These are known as satellite galaxies of the Milky Way. And the word satellite is supposed to make us think of things in orbit. There's nothing static about these patterns that we see in the night sky, at least as long as you're sufficiently liberated about the timescales on which the night sky is evolving. The night sky isn't evolving as far as these kind of images are concerned on human timescales, but it absolutely is evolving. If we go to the other big spiral galaxy in the local group of galaxies, which is a term introduced by Edwin Hubble in 1936 for the galaxies that are in our local group and gravitationally interacting with one another, then the most splendid one we see is Messier 31, also known as Andromeda, which, as you can see, is a really beautiful galaxy. You get a sense of its spiral arms from this image here. But in addition to Andromeda itself, it too has satellite galaxies orbiting around it and in danger of losing out in the gravitational competition with the main gravitational pull due to the much larger mass that is in Andromeda. Satellite galaxies will ultimately get drawn in and they'll orbit through and they won't come out the same way. It won't end well for those smaller satellite galaxies that get pulled in by the very big galaxies, be it Andromeda or the Milky Way. If I now zoom in to the two satellite galaxies near the Milky Way, this is the Small Magellanic Cloud, so called because it was first thought to be some kind of cloud rather than an external galaxy, a galaxy in its own right. And as you can see, no beautiful spiral arms, no pleasing symmetry in its structure. It's very much an irregular galaxy. It's about 4 degrees in extent, and it's absolutely undergoing interaction with the Milky Way now. It's thought that it was once a spiral galaxy, a fairly small one, but those days are long over due to disruption from gravitational interaction with the Milky Way. And this is the Large Magellanic Cloud. Something like the stars in this, if you sum up together the masses of all those stars, you get to something like 10 billion times the mass of our sun. That's actually only about 1% of the mass of the Milky Way galaxy. And the Milky Way is pulling this towards its gravitational centre. Collision is inevitable, but it's not on the list of things that we need to worry about right now, because collision is not forecast to happen for another 2.4 billion years. That's most definitely a problem for another day. But let's get away from the local group of galaxies to bigger, more massive galaxies still. So I'm going to talk now about the so-called elliptical galaxies. And of course, that name comes because of the way they look on the sky. In projection, when we look through a telescope or with binoculars, they look a bit elongated, they look elliptical in projection, but of course, they're ellipsoidal. They're very much a 3D object seen in projection on the plane of the night sky. These galaxies are part of the Virgo cluster, M59 on the right, and M60 is the larger one on the left, just next to a spiral galaxy. Yet more galaxies in the Virgo cluster of galaxies. So galaxies are all around, and many of them are the beautiful spiral structures that I'll come on to shortly. But the ellipticals are remarkable because they seem to be very smooth. But smoothness is not all it seems, as we'll discover later on in this lecture. So perhaps they may seem smooth on the basis of a 12-inch telescope, which is the one used to take this particular image. If you want to get a sharper view still of what the distribution of stars is in an elliptical galaxy, then going out to space is a big help. So using the Hubble Space Telescope and being way above Earth's atmosphere, this particular elliptical galaxy, known as NGC 3610, has an amazingly smooth distribution. But it's not uniform throughout its ellipsoidal structure. On the contrary, it seems to have a bit of an elongated disk, which would have been quite hard to image from the ground unless you had a sufficiently large telescope under sufficiently good conditions. Most of the bright sources in this sky are actually galaxies, apart from the ones with little crosses on them, which are diffraction spikes. They are stars because they appear point-like to the telescope that's observing them. So everything around this image, pretty much, apart from a small number of stars, is a galaxy, but the focus is on this amazingly smooth one. That distribution in brightness profile seems very smooth. It's interesting to comment, by the way, on the word galaxy. It came from the Greek word for milk, which is gala, gamma, alpha, lambda, alpha. Milk, of course, being very smooth and, milk, creamy coloured, of course. So one can understand where the name came from for people who didn't have telescopes or smartphones, of course. So elliptical galaxies seem very smooth, but things are not always what they seem. Let me just take a brief diversion and we'll get right back to galaxies. But on the subject of space telescopes, of which the Hubble Space Telescope has been one of a number of wonderful space telescopes, I wonder if, like me, you watched with excitement on Christmas morning as the James Webb Space Telescope was launched. A truly exciting thing to watch and an absolute tribute to the amazing engineers who just designed that launch and the whole structure so brilliantly. It was a very exciting thing to do, and when it's finally commissioned, we're some months away from that, it will open up deeper studies of the structures of galaxies like this. But in the meantime, while it's on its journey, I decided it would be fun to see if I could watch it. This is an image taken with my Global Jet Watch telescope in Chile, and that linear streak over on the left is the James Webb Space Telescope moving towards its ultimate launch site. It's a complete coincidence that it travelled in front of a star there. But it's an interesting reminder how non-sidereal it moves, how differently from the movement of the pattern of stars it moves. So we've tracked it in other images, and in common with a lot of people, we're happy to see that it's still en route to success. End of diversion on space telescopes. Now let's look at spiral galaxies. Spiral galaxies are the pretty ones. They have amazing structures, as you can see in this beautiful example of Messier 33 shown here. This is another galaxy in our local group. It's third in brightness, after, of course, Andromeda and the Milky Way. And I want to remind you at this point that the structure that you see here is not a static pattern. The gas and the stars within the galaxies are all orbiting around the centre of mass of the galaxy. Those stars and the gas are undergoing revolution around the centre. So this is one example of a spiral galaxy, M33. Here is another one. This is NGC 1300. And what's different about this one, which, by the way, is over 110,000 light years across, this one has a bit of a bar before the spiral arms start. In the previous image, the arms seem to emanate from very close to the centre. But in this one, there is most definitely, again from the Global Jet Watch telescope in Chile, the arms don't seem to start until you get to the end of that bar feature. And this is because the orbits of stars and gas within a spiral galaxy can be, according to the local conditions, can be very unstable. And so that means that rather than preserving the beauty of the spiral arms, they can collapse in and form a linear feature that we call a bar. But that has interesting consequences because you're feeding mass in the form of gas and stars to whatever it is that is at the centre of that galaxy. And of course, that can be a big black hole. And so that can give rise to an active galaxy. But more of that another day. Bars in galaxies are very much a thing. This is known as the grand barred spiral. This is NGC 1365 in the Fornax cluster of galaxies. And if I hold that image in your mind, and this is the neighbourhood for that galaxy. So that galaxy is NGC 1365 in the bottom right. This is the neighbourhood. Anything on this image that doesn't look like a point of course being a star, anything that doesn't look like a point is a galaxy. So the pull that you get is going to influence the other galaxies. And in fact, if you have interactions with galaxy-galaxy interactions, you can induce these spiral structures. These are via so-called tidal interactions, interactions that vary across a particular structure in much the same way that we have a tidal influence from the sun and the moon on the oceans of Earth and on the land of Earth, but we see it most visibly in the oceans of Earth. These tidal interactions can distort orbits and can cause orbits to precess in interesting ways. So let's start by thinking about a circular orbit of a star or stellar cluster within a galaxy on a circular orbit. But of course, it doesn't have to be a circular orbit, and depending on the initial conditions, meaning the initial dynamical conditions and the subsequent dynamical history, you may not have circular orbits. You may have elliptical orbits. I'm not suggesting, or I'm not wishing to suggest, the evolution from circular to elliptical takes this form. I'm just trying to say that there are a lot of different shapes of orbits, lots of different ellipticities or eccentricities of orbits that could be at play. Now imagine that they start to precess around. And as they precess, if they precess differentially from one another, then you can see a structure here that perhaps is reminiscent of the way spiral arms form. What you see here is, on the final frame, I'll keep this movie on loop, what you see in that final frame is a beautiful structure that's reminiscent of the kind of shape that you can get from a harmonograph. But in fact, this is coming from the precession of elliptical orbits all within a galaxy. If only we could observe galaxies evolving on the timescales on which they actually evolve, it would be a wonderful thing. But of course, we can't. But we can, with the benefit of simulations, we can hope to confront, by simulations I mean calculations, numerical simulations. We can hope to verify our understanding of the orbits and the interactions and the structures that they give rise to. So let's now look at some other ways in which tidal interactions can distort orbits and induce spirals. So if the lights go down for this next movie, then imagine we start off with two elliptical galaxies, and as they do that fly past, the differential gravitational forces that they feel rips them apart, but in ways that have beautiful symmetry. And there's something of a simple harmonic motion. It's not that simple, actually, but I hope it reminds you of simple harmonic motion, where gravitational masses attract one another. They fly past, they go out, That potential energy that they have ultimately gets converted back into kinetic energy again. And of course, the dissipation will end up meaning that you see a slightly irregular galaxy, much like this, albeit one with streaks and indeed antennae, that we can hope to match up to observation. So this is a numerical simulation because the timescales on which they happen are vastly in excess of human timescales. But simulations, numerical calculations, transcend our limited view of time by indicating the past and the future of such galaxy-galaxy encounters. And then, I hope you can see, if the lights could possibly go down again, thank you, I hope you can see faint linear streaks here that are absolutely characteristic of this interacting pair of galaxies, which is known as the Antennae galaxy, discovered by William Herschel in 1785. These galaxies are currently going through a star formation phase, what we call a starburst phase, because as they collided together, you've compressed the gas that both galaxies contained, you've increased the density of the gas, and as we know, dense gas, if there's enough of it, and if it's not too hot, will give rise to the formation of stars. So lots of ongoing star formation in those brighter regions of the Antennae galaxy. Now, it was believed for many years, after Hubble constructed this particular diagram, known for fairly obvious reasons as the tuning fork diagram because of its shape, that galaxies would evolve pretty much from left to right across the image, with the very smooth structures being on the left and the pretty spirals and barred spirals being on the right. That was what people used to think. And so now I want to revisit that question of, are galaxies, are elliptical galaxies, smooth elliptical galaxies, all that they seem? Well, again, on the face of it, they look smooth. They don't look exactly like spilt milk, so, the Greek name for them doesn't seem quite right, but nonetheless, we would agree they are smooth and somewhat creamy. Now imagine that you look at these elliptical galaxies not just with an imaging camera, so not just taking a photograph, but you look at them with an instrument called a spectrograph, an instrument that splits up the light as a function of colour or wavelength, which, as I described in my lecture a year ago in the series called Cosmic Vision and called Unravelling Rainbows, when you split up light into different colours and different wavelengths, you get information about dynamics. And dynamics is fantastically exciting. So now imagine that you look all the way across these galaxies, these seemingly smooth elliptical galaxies that I'm showing you here, with an instrument that can split up the light from all the different pixels, all the different regions across each of these galaxies, and address the question, what are the dynamics of that bit of the galaxy relative to us here on Earth? So let's take the central galaxy. Let's imagine we're looking at a particular feature in the spectrum, and you see something remarkable. Some of the gas, that's slightly on the lower left, colour-coded blue here, is moving towards Earth. But the material that's colour-coded red, this, you should regard this as being superimposed on that background image. The dynamical information is imposed on the photograph. The material that's colour-coded red is going away from us. So what you've actually got is rotation. You can see the characteristic signature of the gas and stars coming towards Earth and moving away from Earth. And it's not just this example. It's also in this example here on the right. Unfortunately, the field of view of the particular type of spectrograph didn't cover the entire galaxy. But you can see where it's blue on the left, where it's red on the right, you've got significant revolution. You've got rotation in the gas and the stars. So despite the seemingly smooth appearance of the elliptical galaxies, they are rotating, if only you measure them in such a way that you can see the rotation is there. The actual characteristics of the revolution and the rotation are as different as every galaxy is different. In this case, there's a little bit of a sense of very gentle rotation. On the right-hand side, slightly more dark blue than on the left-hand side. So this right-hand side is slightly, or rather slowly, coming towards Earth. The slight smattering of red pixels on the left-hand side of this right galaxy, rotating away from Earth. So despite the seemingly smooth structures, there is rotation within. And where you have rotation within, that's a bit of a hint of galaxy interactions being responsible for the overall dynamical structure and brightness structure that we see today. So a bit of a modification, indeed an intellectual revolution of the original Hubble tuning fork diagram was called for. And so some work done by one of my colleagues in Oxford, Michele Capellari, has done just that. So rather than saying, okay, well, gradually we go from left to right as galaxies sort of settle down and form these spiral galaxies in their pretty disks, there's more to it than that, unsurprisingly. And rotation, revolution, is the key to understanding those. So really, the axis from left to right isn't so much who formed first, but it's rather how rapidly are you revolving? How rapidly is that galaxy rotating? And it's not just galaxy-galaxy interactions that give rise to revolving, rotating material within. Maybe that's simply telling you about the rotation of that massive gas cloud, which initially collapsed under gravity and on an individual basis formed all the stars within out of that gas, which itself had a net rotation. So for sure, rotation is telling us about a combination of the initial conditions and the ongoing dynamical interactions that a galaxy may or may not have had with its neighbours if it's in a cluster. And so the really fast rotators are indeed the pretty spiral galaxies, the ones that form these amazing structures that I showed you different images of. So this is a very important revision, an intellectual revolution as applied to Hubble's tuning fork diagram, which was a very intelligent suggestion, but of course, in the light of new information, which we now have, spectroscopic information, dynamical information, in the light of that new information, we change our minds. So this was work which my colleague Michele Capellari led as part of a big survey called Atlas 3D, trying to get at the 3D structures, the rotating structures of, it was over 200 galaxies that they investigated in this way to reach the conclusion that is summarised in this diagram on the right. Well, now let's zoom out a bit further still, not just galaxies and clusters of galaxies, but to larger scale structures still. We live in a hierarchical universe. We don't just have clusters of galaxies, but we have hierarchical structures beyond that. We have clusters of galaxies. Everything in the universe seems to be part of something bigger. Earth is part of the solar system is part of the Milky Way is part of the local group with Andromeda and the Large Magellanic Cloud and the Small Magellanic Cloud and M33. The local group is part of the Virgo cluster. But ultimately, you get to these clusters of galaxies. These also are known by the name superclusters. And these can be hundreds of millions of light years in extent and containing millions of galaxies. So we're part of a supercluster. The name of our cluster is called Laniakea, which is a Hawaiian word that means immense heaven. And you can see why the Polynesians of yesteryear would make the association of immense sky. Not that they could observe this, of course, years ago. But this structure itself that we are part of comprises something like 100,000 galaxies stretched out over something like 500 million light years. Contained within this are something like 10 to the power of 17 times the mass of our sun, 100,000 times the mass of our galaxy. These numbers all sort of go over our heads, I think, but it's remarkable to think that we belong to this hierarchy of structures. And this is a sort of quasi 3D mapping of them, of course. But the local group, I should say, is just in blue letters there. I don't know if you can quite make it out with the contrast, but that's the cluster of clusters of galaxies that we are part of. We can project this back on the same original galactic coordinates that I started with at the very start of my talk. You can see the various different clusters, fornax down near me here at the bottom, but various different superclusters, all of which, the membership of all of which can be determined when you know the distances to these objects, which is something that comes from spectroscopy, from knowing what the components are and how far away they are from us. So that is large-scale structure in, by the way, still only the local universe. Well, I want to take a different tack now and talk to something else rather closer to home. And by way of introduction to that, I want to start with something that was rather shocking in the news over the weekend. Shocking in terms of its deadliness to the humans and involved who were directly affected by it, and shocking in terms of the energies involved. I'm talking about, of course, the explosive eruption of the Hunga Tonga Hunga Hapai volcano in the South Pacific that took place. It's estimated that the energy involved in this initially underwater volcano was something like well over 500 times the energy of the bomb that was dropped over Hiroshima towards the end of the Second World War. A hugely energetic event here on Earth. And I mention it because I want to draw your attention to the shock waves, the blast wave, the pressure wave that emanated from this volcanic explosion. So from its location, from the location of Tonga in the South Pacific, the shock wave spread, and within only a matter of hours after the eruption, shown by the red dotted line over on the left, only 6 or so hours later, a pressure hike and suppression, a depression rather, corresponding to the pressure wave, was picked up in a nearby island in the South Pacific, Northern Ireland. It's a bit south of Vanuatu, north of New Zealand. And then in Queensland and in New South Wales, South Australia, and then some hours later, Western Australia, the pressure wave from that explosion was picked up. And it propagated around the world. It was picked up in Gloucestershire and in the Netherlands. That ripple spread around our planet. Such was the intensity, such was the energy of that explosion. And so when explosions happen in space, the consequences of those shock waves and blast waves can similarly be felt and give rise to remarkable transitions in that bit of the universe. And so another shocking, in the sense of startling and surprising, piece of news in the past couple of weeks is what I want to turn my attention to now. It's been realised, it's been established by scientists based at Harvard, that the solar system is at the centre of a newly discovered structure caused by a blast wave. Not by a volcano, but instead by a supernova that happened probably some 14 million years ago. And on its boundary, on the boundary of that blast wave, where, remember, blast waves are pressure discontinuities, much like were measured by the barometers all across Australia, in Gloucestershire, in the Netherlands, in the few slides I just showed you, where you get compression, where you make gas more dense, if it's cold enough, you will trigger star formation. And so the solar system is designed to be indicated by that bright region there. There are these indicated by the sort of bluey lilac regions, are regions of relatively young star formation that were triggered by the blast wave that's indicated in the sort of creamy grey colour. So I'm going to show you now a movie that was prepared by that team at Harvard, led by Alyssa Goodman. First of all, it's just showing you that in the Milky Way, we're getting to us here to the solar neighbourhood, or nearby it, going overshooting and going past it, but something like 14 million years ago, a supernova explosion, from which a big blast wave would inevitably follow. And you can see it expanding because it's overpressured. It expands into outer space. And when it's sufficiently compressed gas, then you can get the formation of stars. So 10 million years ago, up rocks our solar system, which is indicated by the bright light going through the middle, and now we are careering through it. We're not far off the centre now, and so all these different regions in space, Ophiuchus, Corona Australis, Musca, that we can image from Earth relatively easily, these regions we now understood, we knew about these regions of star formation for quite some years, and it had been known that the solar system seems to be at the centre of our void. But the startling announcement of a couple of weeks ago was very much that that void was created by the blast wave of a supernova remnant that gave rise to the amazing structure we see. I do hope that in today's lecture you've got a sense of the richness of the many structures in our universe, but I hope at the same time you haven't just come away with the sense of the richness of the patterns of structure in the sense of brightness distributions and pretty spirals, but also richness in dynamical structure as well. Thank you very much.
So the first question is, I was wondering if galactic clusters flatten, and if they do, what is the mechanism that causes them to flatten?
Right. So why might galactic clusters flatten? Well, if you've got a rotating gas cloud and it forms stars and all that sort of thing, you might then find that under gravity, or you will find that under gravity, those stars will collapse into a disk. And that disk will be swirling in accordance with the angular momentum that the original gas cloud started with. Gravity will act in that direction and the rotation will continue within that disk. So the question is asking, will you see clusters of galaxies flatten in the same way? And it's an interesting question because you might, because flattening comes when you've got collapse under gravity, which isn't to a point because angular momentum is offsetting the collapse and just keeping the swirling, the spiralling, the rotating ongoing. So you probably could maybe pick up a signal of the flattening of clusters of galaxies, but probably what's a more dominant effect is the original distribution of gas throughout the universe. And we know that from that very smooth starting point that I mentioned at the beginning of the lecture, we know that it wasn't smooth at all. But in fact, as it collapses, sometimes it collapses into really quite linear features. And I conjecture that predominantly the shapes that clusters of galaxies seem to span will probably correspond a bit more to the initial conditions of the gas distribution rather than at present to any sort of local flattening under gravity. But it would be an interesting thing to investigate for sure.
Thank you. And a slightly broader question. Do you think that our current climate change could be due to the wobble in the Earth's eccentric orbit round the Sun, rather than CO2 as posited in a recent book on climate?
So this question is talking about the fact that the orbit of the Earth around the Sun is not a perfect circle. I mentioned 2/3 of the way through my talk that we don't just get circular orbits, the ones that I showed in green, but we get elliptical orbits, the ones that are shown in blue. And Earth's orbit around the Sun is indeed elliptical. It has a non-zero eccentricity. But it's not very eccentric. It's not very far from circular. And so modern thinking on the importance of that, I think many researchers throughout the world, people who work in atmospheric physics, would say, again, that's a subtle effect compared with thermodynamics. Thermodynamics is a very well understood science, and the fact that we are trapping more and more heat in Earth's atmosphere because we're changing the chemical composition of Earth's atmosphere by stuffing in more diatomic molecules like CO2, like NO2, like H2O. The more diatomic molecules that are up there, the more they will trap in infrared radiation that, if it could be released into outer space and thereby cool down Earth's atmosphere, you're having a big change on the thermal nature of our atmosphere. You're basically putting a big winter coat on Earth's atmosphere. And that's the dominant effect of why we're heating up. More diatomic molecules, more CO2 in the atmosphere, it will get hot. It's basic thermodynamics. It's akin to the fact that a greenhouse gets hot when it's got summer sun irradiating on it because infrared radiation can't escape, is a precise metaphor for what's going on. So I think that really dominates over any relatively subtle effects in the orbit of Earth, and indeed any subtle variations in its eccentricity. I think they're pretty mild in comparison.
Thank you, Professor. Could I ask something about the blast wave? I imagine a blast wave being an enlarging sphere, which it looked like at the beginning, but very much not a sphere at the end. And was that something to do with where the sort of blast frontier started causing the star formation?
Indirectly. So you're absolutely right. One would expect that a blast wave would be spherically symmetric if the environment into which it was expanding was itself spherically symmetric, was it, or even uniform in extent. However, in the particular case that we see here, there's no doubt that the blast wave that extended left-right, as seen on the slide, encountered much more dense gas than the part of the blast wave that was extending up-down. It looks at, from the fact that maybe there's a tiny bit of star formation, I don't know, or that's a hot pixel on the image, I'm not exactly sure. But essentially no star formation is triggered up-down. And so that tells you in that direction, relative to the original centre of the blast wave, there was basically such a low density, the blast wave went whoosh and didn't do any damage. Whereas left-right, it encountered loads of gas, compressed it, it itself got slowed down, So being slowed down left-right, but able to speed up up-down, gives you that somewhat rectangular shape.
Thank you. I'm afraid we're probably going to have to draw to a close at this point. I wanted to thank Professor Blundell and to thank you all for coming. Please note that her next lecture will be on Wednesday, the 23rd of February, and it is on the magnetic universe. So please do join us for that, and please join me in thanking her once again for a fantastic lecture.